A researcher opens a file. On the screen, static, drawn as a waterfall of grey scrolling slowly downward, and climbing through it, thin and steady, a diagonal line. It has every property it should have: narrow, artificial, sliding across the band at the rate a transmission from another star would slide, because both worlds are moving. Then they open the second file. Same night, 5 minutes later, telescope aimed at an empty patch of sky far from the target. The line is there too, which means it came from here: a phone mast, a satellite passing overhead, a truck on a highway 40 kilometers away with a bad alternator. Between January 2016 and March 2019, two of the most sensitive radio telescopes on Earth listened to 1,327 nearby stars. 10 years of planning behind it. $100 million. That moment, the diagonal line and the collapse, happened 6,154 times. Every one of them came from Earth. The result was zero, and then the zero turned out to be far larger than the people who built it had realized. Not because somebody found a signal later, because of where those two telescopes had been listening without anyone noticing. The paper landed in the Astronomical Journal in 2020, led by Danny Price, an astronomer at the University of California, Berkeley. The title reads like a filing reference: Observations of 1,327 nearby stars over 1.10 to 3.45 gigahertz. Written by people who expect to be quoted against their will for the next 40 years, and who left nothing in the sentence for anyone to grab. Their conclusion runs to a single line. After removing every event with characteristics consistent with terrestrial interference, they were left with zero candidates. Zero. Not a maybe, not an anomaly held back for a second look, not a signal under review. Zero. Price and his team treated that as a finding rather than a disappointment, and they published the number a finding like this buys you. A ceiling on the power of any radio transmitter aimed our way from those stars, at those frequencies. 2 trillion watts through the green bank dish, 9 trillion through Parkes, which is smaller and therefore less forgiving. Hold on to the first figure. It comes back in the second half of this video, and when it does, it stops being a footnote and becomes the whole story. 2 trillion watts sounds like a number chosen to impress. Here is where it sits. Every power station, every engine, every furnace on this planet, running at once, adds up to something in the region of 20 trillion watts. The ceiling they published is roughly a tenth of the total energy output of human civilization, transmitted continuously, pointed at us. That is the scale this search operates at, and it took 60 years to get there. In 1960, a radio astronomer named Frank Drake aimed a dish in Green Bank, West Virginia, at 2 stars. He listened across a few months on one narrow frequency. He heard a single promising signal, chased it, and traced it to a passing aircraft. The project was called OSMA, 2 stars. It is where the entire field begins. 2 stars, Tau Ceti and Epsilon Eridani. Both close, both roughly sun-like, both picked because they were the only reasonable options a single dish could reach in a season. What Drake did was small, and the size was never the point. Until that spring, whether anyone else existed had been a question for philosophy, argued with reasoning and belief. After that spring, it became a question you could answer by pointing a piece of metal at a coordinate and writing down what arrived. Then the field spent 30 years being embarrassing to fund. Observatory directors kept the work off the front page of their proposals. Nobody listed it as the primary science case, because the primary science case is what a review panel reads first. In 1993, the United States Congress killed NASA's own search program within a year of it switching on, and for the next 2 decades the work survived on private money, donated hardware, and telescope time borrowed from projects that were about something else. 60 years of listening, funded like a hobby. Which brings us to the Ghost, August 1977. A dish in Ohio nicknamed the Big Ear recorded a burst of narrow-band energy that towered over the background and lasted 72 seconds. An astronomer named Jerry Eman found it on the printout days later, circled the characters in pen, and wrote one word in the margin. They swung everything they had back to that patch of sky. It never came again. Half a century on, those 72 seconds remain the most famous moment in the history of the search, and nobody can say what they were. A single detection, never repeated, cannot be confirmed and cannot be ruled out. It can only be remembered. That is what Breakthrough Listen inherited. 60 years of small campaigns, one unrepeatable ghost, and a question that nobody had ever asked at industrial scale. Breakthrough Listen is a 10-year, $100 million program hunting for technology, for a transmitter, for something that is deliberately, physically broadcasting. It bought time on 2 instruments, and the choice tells you how seriously it was meant. The first is the Robert C. Byrd Green Bank Telescope in West Virginia, a steerable dish 100 meters across, standing inside a federally protected zone where radio transmission is restricted by law. Houses in the nearest towns run on wired telephones. Site engineers drive diesel vehicles because the spark plugs in a petrol engine throw off enough interference to register on the instrument. An entire region of a modern country has been kept artificially quiet for decades to protect the hearing of one machine. The second is the Cirro Parkes Telescope in New South Wales, Australia, 64 meters of dish that has been pulling faint signals out of the southern sky since the 1960s. Drive into that valley and your phone stops working before you reach the gate. There is no coverage to lose. The restriction is written into federal law. It has held since the 1950s, and the people who live inside it have built a life around a machine, listening for something that has never once answered. Between them, over 3 years, they worked through a target list. 1,138 stars at Green Bank, another 189 at Parkes, 1,327 in total, all of them chosen for one reason above every other. They are close. The wider program has a target list of 1 million stars. These 1,327 are its inner core, the volume-limited sample, the nearest and best characterized objects on the sheet. Most of them sit near enough that a signal leaving today would arrive within a human lifetime, and a signal arriving now departed recently enough that whatever sent it could plausibly still be there. Those were the best odds anyone in the history of the question had ever been able to buy. Here is the problem with listening for a transmitter. Earth is screaming. Mobile phones, aircraft transponders, satellite downlinks, radar installations, a microwave oven with a worn door seal. All of it pours energy into the same bands a telescope is straining across. The dish at Green Bank is sensitive enough that engineers treat a mobile handset inside the site perimeter as a serious contamination event. Aimed at a star 40 light-years out, it will happily record a 2-way radio on a road 40 kilometers away, and the signal itself carries no label saying which one it is. Hearing something is trivial. Everything is something. The work is proving that what you heard came from somewhere other than here. Their method for that is old, and it is elegant. You point the telescope at the target star for 5 minutes. Then you swing it away to a different patch of sky for 5 minutes. Then back on. Then off. On. Off. All night, the dish nodding between the star and the void beside it. Anything genuinely arriving from that star appears in the on-target blocks and vanishes in the off-target ones. Anything generated on Earth leaks in through the side of the dish and sits in all of them, indifferent to where the machine is aimed. Then there is drift. Earth spins on its axis and races along its orbit. A planet around another star does the same. 2 accelerating platforms mean a signal sent from another world arrives here, sliding slowly across the frequency band, in the way a passing siren slides in pitch. A signal that holds perfectly still is almost always traveling along with us, which makes it ours. Those 2 tests carry the entire discipline. Everything else is bookkeeping. Run that machinery across 3 years of recordings, and the raw output is overwhelming. More than 51 million detections crossed the threshold. 51 million individual moments where something rose above the noise floor and the software wrote it down. Almost all of it is the ordinary electromagnetic roar of a technological species talking to itself, arriving from a few hundred kilometers away rather than a few 100 trillion. The automated filters went to work. Anything present in the off-target blocks, discarded. Anything sitting rigid at a fixed frequency, discarded. Anything parked on a channel already known to belong to satellite constellations, air traffic control or ground services, discarded. 51 million became 6,154. 6,154 clusters of events that the machines could no longer explain away on their own. Then human beings opened every single one. This is the part nobody films. Someone loads the plot, sees the diagonal climbing through the static, and for 4 or 5 seconds it looks exactly like the thing everyone in the building has spent a career waiting for. Then they check the off-target file. Then they check whether the same frequency showed up on an unrelated star on an unrelated night. Then it collapses, 6,000 times, 6,000 small collapses, spread across 3 years, absorbed by people who kept opening the next file anyway. Nobody in that building ever got to be the person who found it. They got to be the people who proved, one plot at a time, that it had not been found yet. And the team did something with those events that deserves attention. Rather than quietly deleting them, they published their best-looking cases, with coordinates and frequencies attached, in order that anyone else could pull the same data and argue with them. Everyone traced back to Earth. What does a zero like that actually mean? Here the field splits, and it has stayed split ever since. 3 explanations compete. None has been eliminated. The paper refuses to choose between them, and the authors say as much in print. The first is the one everybody reaches for. Nobody is there. The stars run on chemistry and physics and nothing else, and the galaxy is a magnificent empty machine that we happen to be standing inside, talking to ourselves. It is the cleanest explanation and the one the data supports least, which is an uncomfortable combination. A zero across 1,327 stars is exactly what an empty galaxy looks like. It is also exactly what a crowded galaxy looks like if the neighbors are quiet or distracted or pointed somewhere else. The second is harder to live with, because listening harder will never defeat it. Somebody may be out there and still fail the test. Consider our own trajectory for a moment. Earth's shift to fiber optics, to tightly focused satellite spot beams, to compressed and directed signals has made this planet quieter in these bands over 30 years. The window during which a civilization sprays its conversations across interstellar space might be a century wide. A species 200 years ahead of us could leak almost nothing at all. Even a species that stayed loud would have to be loud on an extraordinary scale. 2 trillion watts is a deliberate beacon, engineered and paid for by somebody who decided that being heard across light years was worth a permanent slice of their power budget. Ordinary broadcasting falls many orders of magnitude short, and a beacon has to be aimed. A beam is efficient precisely because it is narrow, which means anything narrow enough to be affordable is narrow enough to sail straight past us. There is no reason to assume a stranger's beam happens to land on one unremarkable star in one unremarkable arm of the galaxy. Then there is time. Across the whole campaign, most of these stars were watched for a matter of minutes. A transmitter running 1 hour a year would need extraordinary luck to be caught, and luck was in short supply. The third explanation is the one working astronomers reach for first, and it is the least dramatic and the most corrosive of the 3. 1,327 is a rounding error. The Milky Way holds somewhere between 100 and 400 billion stars. Drawing conclusions about the galaxy from 1,327 of them is like lowering a bucket into the Pacific, finding no fish in it, and publishing on the absence of marine life. That comparison has followed this field for 60 years. It shows up in reviews, in funding committees, in the comments under every article ever written about the subject. It is the reason most people quietly stopped taking the search seriously. In 2020, a second team opened exactly the same recordings and found the flaw in it. 3 people, Michael Garrett and Andrew Simeon, working with a student named Bart Wlodarczyk-Sroka, and the thing they noticed had been sitting in the open since the first night of observing. A radio telescope never sees a star, it sees a cone. Aim a 100-meter dish at a target, and the instrument collects everything arriving from a patch of sky, and that patch has width. Astronomers call it the beam. The beam behaves like a searchlight rather than a laser pointer, which means that behind the target star, further out along the same line, there are other stars, fainter ones, more distant ones, objects nobody proposed, nobody argued for in a telescope time allocation meeting, nobody wrote onto the sheet. Their light poured into that dish for the full duration of every single observation. They were in the data the whole time. Nobody had counted them. Counting them had been impossible until recently, for a mundane reason. To say anything about a background star, you need its distance. Distance is what turns a signal strength measured at the telescope into a transmitter power at the source. Without it, the star is a dot with no address, and no statement can be made about what is happening there. Then Gaia arrived. The European Space Agency's Gaia mission spent years measuring positions and distances for more than 1 billion stars using parallax, the same trick your two eyes perform to judge depth, scaled up to a baseline the width of Earth's orbit. Watch a star from one side of the Sun. Watch it again 6 months later from the other side. Measure how far it appears to shift against the background, and geometry hands you the distance. For the first time in the history of astronomy, a catalogue existed that could put an address on almost anything faint and nearby. The three of them took the breakthrough listen observations, laid every telescope beam over the Gaia catalogue, and asked the question nobody had asked. How many stars were inside these fields? 288,315. Not 1,327. 288,315 stellar objects had been observed. Same telescopes, same nights, same recordings, already sitting on the same hard drives. Not one additional minute of observing time. Not one additional dollar of funding. Not one new photon. There is something quietly unsettling about that. Telescope time is the most contested resource in astronomy. Nights are fought over in committees, scheduled years ahead, lost to weather and hardware failures and a bad receiver. And 250,000 stars had already been surveyed, sitting in an archive, waiting for somebody to remember that a field of view has width. Every one of them was silent too. Now go back to the bucket in the Pacific. The sample did not creep upward by 10%, it did not double, it grew by a factor of more than 200. The zero became 220 times larger than the people who produced it had realized, and the strongest objection to the entire field lost most of its force overnight, without a single new observation. The paper is honest about what that costs. Background stars sit further away, which means a transmitter out there would have to be far more powerful to have registered at all. Extending the sample buys nothing for weak signals. It buys an enormous amount for enormous ones, across an enormous volume. And here is the number that had never existed before. Within roughly 160 light-years of Earth, fewer than 7 star systems in every 10,000 are running a continuously operating transmitter of that class, aimed in our direction. Push the volume out to 650 light-years, where only the most extreme beacons would ever have shown up, and the constraint holds at fewer than 4 in every 10,000. 7 in 10,000. That is a boundary, drawn on a map, with an error bar attached to it. Somewhere in a server rack, 219 terabytes of that silence are sitting on disk. Every second of it was released publicly. Anyone with a connection and enough patience can download the recordings and go looking for the thing the original team missed, which is precisely how the second paper happened. That archive is the actual product of the search. Not a photograph, not a moment. A physical volume of stored nothing with coordinates attached that shrinks the region where an answer can still be hiding. It is the least photogenic object ever produced by a $100 million program, and it is the only part of it that will still be useful in 300 years. Science does this constantly and never gets credit for it, because absence photographs badly. Particle physicists spent decades failing to find the Higgs boson, and each failure carved another slice off the range of masses where it could still be sitting. By the time they built a machine specifically for the corridor that remained, the corridor was narrow enough to search properly. The discovery was standing at the end of a hallway built entirely out of places it had already been ruled out of. This search sits near the start of that same process, and the honest position is that it has barely begun. We have proven nothing about whether we are alone. Every author involved states that plainly in print without hedging. What has been established is smaller and firmer than that, and it holds up. High-powered, continuously running radio transmitters, aimed roughly our way, in these particular frequencies, during these particular 3 years, are uncommon in our stellar neighborhood. 6 qualifiers in one sentence. Every one of them, a door still standing open. The space that remains is enormous. Frequencies nobody has examined at this depth. Optical pulses, beacons that fire for an hour a year, civilizations that never built a radio, or built one and abandoned it before we came down from the trees. Stars nobody has pointed anything at, which is nearly all of them. But the perimeter around that space has moved, and unlike almost everything else produced in a given year of science, a measured absence does not expire. Theories get overturned, models get replaced. An absence, recorded with a known instrument at a known sensitivity across a known band, stays exactly where it was put. It will still be true in 1,000 years. Whoever comes next starts from its edge. Think about what happened here. A species that has existed in its current form for a few 100,000 years, on one planet, around one ordinary star, built 2 metal dishes and pointed them at the dark. It listened for 3 years. It recorded 51 million moments that turned out to be its own noise coming back at it. Then it returned to those recordings, laid over them a map of the sky it had only recently finished drawing, and discovered it had accidentally been listening to 250,000 suns the entire time. Nobody rang a bell, no press conference, no photograph, no headline anywhere on Earth. The result was a table in a journal, describing a region of the galaxy where a particular kind of neighbor has been ruled out. That is what looking looks like from the inside. A slow, unglamorous narrowing of the places an answer can still hide, carried out by people who will almost certainly die before the question is settled, and who did the work anyway. Frank Drake aimed a dish at 2 stars and heard nothing. 60 years later, 250,000 stars have been checked, and the sky is still quiet. Read one way, that is 6 decades of failure. Read another, the searchable volume of the galaxy has shrunk by a factor nobody in 1960 would have believed was reachable inside one human lifetime. That is either a defeat or the most patient thing our species has ever attempted, and I think it might be the second. The recordings will outlast everyone who made them. Somebody will open that archive in 100 years, with instruments we have no name for yet, and begin at the edge of the region we cleared. The sky is not empty, it is unexamined, and every silence we measure properly is one less place left for the answer to hide. Thanks for watching, and I'll see you in the next one.